Hello students, in my previous lecture I have discussed about the moment distribution method with 2-span continuous beam and 3-span continuous beam with different end condition. Now moment distribution method is most important for the frame structure. We can solve, we can analyze any beam with the help of slope deflection method and moment distribution method. But for the particular frame analysis, moment distribution method is most suitable method. So in this lecture we will discuss about the how we can analyze the frame structure using moment distribution method. In moment distribution method we know about the steps, but still I will discuss here again the steps, and after that we will discuss about the frame. So as you know, this method is developed by Professor Hardy Cross in 1932. The method solved for the joint moment in the continuous beam and rigid frame by successive approximation. Some of the important terms that also we discussed. First is stiffness, that is known as K. The moment required to produce the unit rotation at the simply supported end of the member is called stiffness or absolute stiffness. The stiffness is equal to moment upon rotation. So K is equal to m by theta. But theta is unit, because here we discussed about the unit rotation. Means unit rotation is theta is equal to 1. That's why we can consider K is equal to m. Now here you can see this is our beam and this is our point A. Here we will discuss about this moment. Now proportion in which far end fixed. Suppose I am talking about this moment and far end fixed, then what is the effect of moment over here? M is equal to K is equal to 4 EI upon L, right? That we know. The moment produced for the far end will be equal to 2 EI upon L in the same direction. Now proposition number 2, far end simple. If we are talking about this moment and far end is simple, then moment of here at point A is 3 EI upon L. Means the moment required to rotate the near end of the prismatic beam through the unit angle without translation, the far end being simple, is given over here. Now you can consider moment 0 over here, and moment here is 3 EI upon L. This is also known as the stiffness. Again, the most important thing, that is carryover moment. In the beam with far end fixed, if the moment is applied at the near end m dash, the moment produced at the far end, this moment is called the carryover moment. Means here we have to carry over the moment at the next end with the end condition. For the beam with far end fixed, then we know m is equal to 2ei upon n and the far end is m dash 2ei upon n, but it is simple, then moment is 3 and 0. So what we can consider over here, suppose our far end, on that point we want to distribute our moment with the help of carryover. So at that time, far end fixed or continuous, then we will transfer the half of moment over there. But in simple support, it will be 0. So at that time we doesn't transfer the moment over there, where m is the applied moment at the near end and m dash is carry over moment. Now from that we can find out the overall moment at joint, that is called carryover factor. For that we have to find out the carryover factor, and for that it is m upon m dash, that we know. For far and fixed, then m dash is 4ei upon l, and that is 2ei upon l, means it is 0.5, and for simply supported it is 0. Now distributing factor, it's called distribution factor. Here we have taken some small example for the understanding of this. As we discussed, this is our common joint from here to here, one beam, here to here another, third, fourth. Total 4 number of beam are connected at a single joint. The end condition of all the members are different. So the moment is generating in this particular beam, and which is given stiffness in the form of moment is difference. Suppose we are talking about the K1, right? It is O to A, means it is here, and the far end is fixed, means A is fixed. At that time K1 is equal to 4ei upon L. K2 is simple, then it is 3ei upon L. It is 4ei upon L, it is 3ei upon L. This kind of all stiffness we can finding out with the help of far end condition. So now we can finding out the total sum of this stiffness. So distribution factor is carried out by k upon sigma k, right? For the distribution factor OA member, it is k upon sigma k. So we can finding something like this. For OB, k2 upon sigma k, then it is something like this. Again k3 upon sigma k, k4 upon sigma k. This kind of all joint moment we can carry it out by the distribution factor, and once we can get the distribution factor and carryover factor, then we can calculate the whole system that we know. Now next important thing, the friction moment. As you know, in slope deflection method we have also calculate the friction moment. Again in moment distribution method we have to find out friction moment, right? This friction moment is considered as our individual span is fixed. After that we can finding out unbalancing moment, the sum of the friction moment meeting at a joint which is initially clamped at 0. The distance between 0 and sum of this moment is called unbalancing moment. So this unbalancing moment must be distributed in some way that it is getting same at the particular joint. So distributed moment, the unbalanced moment causes the joint rotation when it is related. The resistance to rotation will be produced from the member of proportion to their stiffness. The resisting moment developed in the member are called distributed moment. Okay, good. And relative stiffness, when several members meeting at a joint have difference and conditions of support and their end, it is always convenient to express the stiffness of the member in the term of relative stiffness that we discussed. Relative stiffness is most important part of this moment distribution method, because from the basis of this stiffness, moment will be distributed from one joint to another joint. So relative stiffness is most important part for us. Now sign convention, it is again most important thing. support moment means end moment, anti-clockwise and clockwise. Two type of moment is there. Suppose this is anti-clockwise, means it is negative. This is clockwise, it is positive. Rotation, slope, we know when force is applied on particular beam, it will be rotate something like this. Then clockwise rotation is positive, anti-clockwise rotation is negative. Sinking, settlement. As right hand side sinking of particular span, then it is positive, and left hand side it is negative. So dear student, when sinking is occur, whenever the support means column is settled down due to some heavy forces or else unbalancing of ground. So settlement is done in our span. So at that time we have to consider that sinking for the analysis of continuous beam. Clear? This kind of condition is occur. Now, fixed end moments. You know what is fixed end moment, how it is calculated, and here when we are going to analyze any continuous beam, then it is must noted that the fixed end moment is our initial part, and that moment must be unbalancing our member. We have to balancing that member with the help of rotation and the stiffness. So what is the fixed end moment? This is our simple single span and the point load at the center. At that time fixed end moment is anti-clockwise, here it is clockwise, and the value is WL by 8, and here also WL by 8, but it is minus and it is plus. Second case, fixed beam with UDL over the entire span. This is anti-clockwise MFAB, this is clockwise MFBA, and the equation is WL square by 12. Here it is minus, and again here it is plus WL square by 10. When the eccentric point load is acting somewhere at point here, means at a distance from left support and from right hand support, it is B, then anti-clockwise moment and a clockwise moment as a fixed end moment is generating over there, and the equation is WAB square upon L square is minus and plus WBA square upon L square, right? Same way this kind of UVL, if UVL over there, then fixed end moment MFAB and MFBA. MFAB is equal to WL square by 20 and MFBA is equal to WL square by 30. It is minus and it is plus. If moment is there, then the equation is this. So whenever which kind of condition is acting on our beam or on our frame, then we have to take fixed end moment from this table. This fixed end moment is our initial moment for finding out the next thing. Again, these two things is most important when our beam is fixed, and here the clockwise moment is both generating due to fixity, and it is 4 EI theta by L and 2 EI theta by L as we discussed as a stiffness. Here far end is simple, at that time fixed end moment 3 EI by L square and MFBA is equal to 0. So which are the steps for finding out the moment distribution method and slope, shear force and bending moment? First we have to finding out the fixed end moment at each member. After that, finding out the distribution factor for the various member meeting at the different joint. If our end support is simple, then distribution factor is directly taken as a 1. But if it is fixed, then distribution factor is 0. After that, we have to preparing a moment distribution table. In that table, we have to distribute our moment with the help of distribution factor at a particular joint. At each joint, find out the unbalancing moment, distribute to then at the joint according to the distribution factor so that they are balanced. This is called as a distribution. There is no unbalancing moment at any joint in any cycle. First cycle is completed. In that case, we have to generating or rotating our cycles for the carryover distribution. Carryover distribution, whenever it is value at the particular point, so the value is nearby 0, then we will stop this cycle. The distribution moment is carried over the other end of the member which the same sign, so called carry over. The cycle may be repeated depending on the accuracy desired. The final moment may be found at the summing of all the moments in each column, means at each joint. At the intermediate joint, the sum of moment must be 0 at desired by the equilibrium condition. At internal joint, sum of distribution factor is 1. This is the most important point. Whenever we are talking about some joint, at that time, the sum of this distribution factor must be 1. Suppose we are talking about the B, means B to A distribution factor is alag, B to C distribution factor is alag. But what we are going to do, sum of that distribution factor must be 1. Now here we are talking about the portal frame, right? Portal frame with side sway, without sway. We have to consider which kind of frame is given here. If it is a sway, then analysis is different, and if it is non-sway, then we can simply calculate as the beam. In the case of frame with loading, symmetrical and geometrical symmetry, there will be no side sway. The joint of such frame are subjected to rotation only and no translation. The lack of symmetry of either in geometry, the loading, however, they cause the frame side sway. Means if it is difference from the symmetrical, then it must be causes side sway. How? First, unsymmetrical loading means asymmetrical loading is there, then it is sway. Unsymmetrical outline of portal frame. Some of the column is different size and other column is different size. Different end condition of column. One of the column support is fixed and another is hinge. Non-uniform section I and 2EI, it is different, then it is a sway. Horizontal loading on column. If it is all kind of the symmetrical, but horizontal loading is there, means it is causes side sway. Settlement of support, one of the column is settled down, then it causes side sway. So this kind of sway is generating in our frame and it causes side sway. When the joint of the portal frame sway at the set of moment are produced at the two column head, the ratio of that sway moment at the two column head will be depending upon the end condition. Let's now take the different end condition to find the ratio of the side sway. For the calculation of side sway analysis, we must have to take the ratio of these two column moment with the end condition. Suppose here both end hinge, means here also a hinge and here also hinge. Then moment of BA, what it happens, it is 3 EI delta upon L square, as we know. Here also 3 EI delta upon L square. The I is different, length is different, then we can get the some ratio of these two moment which is used in calculation of moment. Now, if both the ends are fixed over here, then moment from B to A is equal to 6 EI delta upon L square, and here again 6 EI delta upon L square. But I is different and length is different, and we can get the sum value for the ratio. Now, one end is fixed and another end is hinged. At that time, the equation is minor different. MBA is equal to 6 EI delta upon L square, and MCD is equal to 3 EI delta upon L square. Length is different, I is different, then the ratio of this is totally different. So, dear student, from this ratio we have to again making second moment distribution table for the sway analysis, and it will gives us the another moment for the sway analysis. Clear? So in this lesson you can understand how we can find out the ratio of the two column for the analysis of sway. So it is most useful for the finding out the moment for the frame analysis. Thank you.